When space exploration was making its first steps, the Soviet Union and the United States focused on rockets. The satellite was almost an afterthought. Sputnik was a transmitter designed to let the world know that it was there. The American Xplorer 1 had a radiation detector, but only an accidentally high orbit allowed it to detect the Van Allen radiation belts. Clearly, there was much to learn about making spacecraft. Soon, engineers were designing probes that had to function in deep space for years, but it would take decades for the technology to catch up with the ambition. When Caltech's Jet Propulsion Laboratory was absorbed into the newly established NASA, it was given responsibility for the building and operation of robotic spacecraft. NASA's initial focus was the Moon, and JPL started designing a series of Ranger spacecraft to photograph the Moon. It was not until 1964, after 6 consecutive failures, that Ranger 7 successfully returned pictures of the lunar surface. It had been a bruising experience for NASA and for the team at the Jet Propulsion Laboratory, but the lessons learned gave engineers a realistic understanding of the conditions their machines would have to withstand. The Jet Propulsion Laboratory had been working on a new spacecraft. NASA was aware that an opportunity to launch to Venus would occur during July and August of 1962, but the new Mariner-class probe would not be ready in time. They began reworking the Ranger concept for the interplanetary mission. They were called Mariner R spacecraft. As was becoming clear to everyone, space hardware was still unreliable, so duplicate Venus attempts would be made. Mariners 1 and 2 would launch toward Venus on the troubled Atlas-Agena combination. Some felt these missions were doomed from the beginning. Mariner 1 lifted off in July 1962. Just 5 minutes later, as it was veering off course, it was destroyed. The problem was a software error. 1 month later, Mariner 2 launched successfully. The spacecraft, on its path to Venus, would have to function autonomously in deep space for at least 100 days. The probe was designed with no redundancies. A range of mission-critical functions had to go perfectly for the Venus observations to happen. Data could not be recorded on the spacecraft. It was transmitted to Earth via the Deep Space Instrumentation Facility, the precursor of the Deep Space Network. It soon became obvious that while Mariner 2 was functioning, it wasn't behaving as expected. The Earth sensor was only just able to see the Earth. Its output was so low that as the probe continued toward Venus, it would stop knowing where to point, and all contact would be lost. After 35 days in space, the output of the sensor returned to normal levels. Even today, nobody knows why. This was just one instance of Mariner 2's unexpected behavior. Spacecraft engineers understood with such a long-range mission, fine adjustments would need to be made to the probe's trajectory. The spacecraft had its own engine for mid-course corrections, but this was early days for such a maneuver, And while the correction was reasonably accurate, the JPL team was frustrated by gaps in the telemetry data the probe was unable to send. In December 1962, as Mariner 2 approached Venus, the probe had problems. One of its solar panels had failed, several telemetry sensors had gone dead, and the spacecraft was overheating. As it passed Venus, Mariner 2 made a 42-minute scan of the planet, but it had no cameras and could not return images. It discovered Venus had a slow backward spin. It had a predominantly carbon dioxide atmosphere at high pressure with very hot surface temperatures. All science instruments had functioned as planned, returning data at a modest 8 bits per second. The nation celebrated. This was the first time the United States had achieved something in space that the Soviet Union had not already done. William Pickering, the director of JPL, was feted in California's Tournament of Roses parade. 20 days beyond Venus, Mariner 2 died. But at JPL, a radically new idea was taking shape. Doctoral student Gary Flandreau was plotting the paths of the outer planets when he realized that a single probe launched in 1977 could reach Jupiter, Saturn, Uranus, and Neptune with a flight lasting just 8 years. He published a paper, yet the idea was slow to catch on. At that time, all that was known of Jupiter and Saturn came from ground-based telescopes, and the technology of the day could just possibly carry a probe to Jupiter. Astronomers were keen to have a closer look, and the Grand Tour was the most immediate way to learn more, but it would be expensive. Plans emerged for a new Mariner spacecraft that incorporated the latest 1970s technology with every successful design feature that JPL had pioneered. 4 of these probes, all launched at carefully selected times, would visit the planets beyond the orbit of Mars.
But the time has also come for emphasis on developing better ways of managing what we have.
Under the Nixon administration, the focus had shifted from space science to space business, and a new reusable space shuttle would cut the cost of launches and give NASA a monopoly in the low Earth orbit market. Because of its billion-dollar price tag, NASA cancelled the Grand Tour. New science missions to the planets were to slip in priority, though existing plans would continue. Early in 1972, there was good news from Washington. A scaled-down version of the Grand Tour had been approved. Now called Mariner Jupiter-Saturn, a mission with just 2 spacecraft would visit Jupiter and Saturn, with a possibility that one probe might fly on further. JPL engineers made sure that the probes would be capable of an extended mission stretching to Neptune. Ultimately, these were to be known as the Voyagers. The spacecraft would have to function in deep space for at least 12 years. Subsystems had redundant backups that could be brought online should a primary system fail. Traveling away from the sun, power from solar panels was not an option. The Voyagers were powered by the natural decay of plutonium-238. But could a spacecraft last that long?
Minus 15 seconds and counting.
In something the press found difficult to understand, Voyager 2 was launched first.
9, 8,
Its slower path to Jupiter would allow it to pass all the giant gas planets.
2, 1. We have ignition and we have liftoff.
Voyager 1, which launched 16 days later, would actually arrive at Jupiter first. Right from launch, flight engineers were monitoring the behavior of Voyager 2. Even as it was firmly attached to its Titan III launcher, the spacecraft began switching to backup systems. As the booster rolled on its axis, the probe, sensing a fault, transferred to its secondary gyros, then to its secondary computer. The fault protection system was doing what it was programmed to do, but it should not have become active until it had separated from its launcher. In rapid succession, the fault protection system kept flipping to backups. Stage separations happened as scheduled, but the spacecraft remained confused. On the ground, debate started about what the best course of action would be. After the boost phase had finished, Voyager 2 began unfolding its science booms. When it separated from the upper stage, the spacecraft was left tumbling, unable to find the Sun and its reference star Canopus. Ground staff elected to leave Voyager 2 alone, and eventually the fault protection system, which was now fully in control, sorted through its options and the craft stabilized. "16 days later, its twin, Voyager 1, launched. This time, there was a fuel leak in the Titan launcher, which caused it to underperform. The Centaur second stage was able to compensate for the low velocity by burning for longer, sending Voyager 1 safely on its way. The engines finally cut off with just 3.5 seconds of fuel left. Both Voyagers were on their way to Jupiter, but until they arrived, which would be almost 2 years, they would have no public profile. NASA was coming to grips with what was involved in making a reliable spacecraft. It took careful design, and it took rigorous testing of all components. Washington saw that it took $1 billion, and politicians were reluctant to embrace the free spending of previous decades. In deep space between Mars and Jupiter, both the Voyagers had developed problems. On Voyager 1, the scan platform, responsible for pointing the spacecraft's cameras, was not operating smoothly, sometimes jamming, threatening its ability to capture images. On Voyager 2, the primary radio receiver had failed. Fault protection had switched to the backup, but this unit was no longer able to follow subtle changes in radio frequencies. Mission Control understood the problems and implemented corrective measures. The mission would continue. In January 1979, Voyager 1 approached Jupiter. Its atmosphere was swirling with storms and complex eddies. The world was stunned by the intricate beauty of Jupiter. Only the large 64-meter antennas could communicate with the Voyagers. Images and data could be relayed directly to Mission Control, but during planetary encounters, data accumulated at such a high rate that most was recorded on the spacecraft's digital tape recorder for later transmission. The 8-track recorder could store just 64 megabytes of data. A peculiar plume above Io was a volcanic eruption. The small inner moon in the Jovian system is the most volcanically active body we know. Several months later, as Voyager 2 reached Jupiter, it was able to target different areas. The ice moon Europa featured strange cracks. and the Voyagers discovered that Jupiter had a faint set of rings. As the Voyagers left Jupiter, headed for Saturn, a new term gained currency. The Voyager mission was now referred to as a flagship program. Now there was great public interest in Voyager. During the next 2 years, as the Voyagers journeyed to Saturn, planetary researchers began trying to understand the mountain of data the spacecraft had returned.
We've got 27.473.
In the 1980s, because so much of NASA's budget was tied up in the Space Shuttle program, very few new planetary missions were envisioned. One exception was the Jupiter orbiter and probe. This concept had gradually been taking shape since 1975. Initially known as JOP, it was renamed Galileo in 1977 and was scheduled to launch in 1982. The growing importance of the shuttle to NASA meant probes like Galileo would be deployed from the shuttle's cargo bay and then sent on their way via a Centaur upper stage. Late in 1980, Voyager 1 was approaching Saturn. Again, the images were stunning. The complexity in the rings was unexpected, and Saturn was radiating more energy than it absorbed. An important target for Voyager 1 was Saturn's moon Titan, the only moon in the solar system to have a substantial atmosphere. However, any surface features on Titan were obscured by thick haze. The spacecraft's instruments suggested that the moon could have lakes of liquid methane. After Titan, Voyager 1 looped up above the plane of the planetary orbits. It would not be able to reach the other outer planets. As it departed, it captured a final image looking back at Saturn. 9 months later, Voyager 2 arrived at Saturn. Mission planners were able to build on preliminary observations from Voyager 1 so that the second spacecraft could closely target features of note. Initially, the moons orbiting Saturn were of only passing interest, but no one expected them to differ so greatly. The tiny moon Enceladus is covered in clean water ice. It's the most reflective body in the solar system. Each of the planetary encounters attracted public enthusiasm, and the Voyager science team organized daily press briefings that were broadcast live. Images were distributed as photographs with a brief description taped to the back, and JPL staff worked long hours to meet press requirements.
Just for the moment, let me show
Management understood that public backing for planetary science made it easier for political leaders to maintain funding.
Red, you're seeing a lot of haze, and where it's blue, it's relatively free of haze.
Yet the publicity generated by the Voyager program was masking the absence of planning for future planetary missions.
And seeing more haze, and so we see this.
The Galileo orbiter was nearing completion, but in 1981 it was threatened. Ronald Reagan had become president, and he had promised to cut the deficit, to cut taxes, and to increase spending on defense. The Office of Management and Budget wanted to cut the expensive Galileo program, but it was saved by the Pentagon. The Air Force was interested in its autonomous functioning and its radiation-hardened electronics. By the end of 1982, the Space Shuttle had finished its test flights and was now in service. Because the Centaur upper stage had a sound record when working in tandem with Atlas and Titan launchers, politicians could not see why that good performance would not continue when it was used inside the shuttle. So the final decision was made in Washington. Deep space missions would launch with Shuttle Centaur. Finally, in 1985, Galileo began the first stage of its journey to Jupiter on the back of a truck headed for the launch complex in Florida. Late in 1985, Voyager 2 began its approach to Uranus. During its cruise phase, after leaving Saturn, the imaging team had been rewriting software to help the cameras deliver sharp images. The light at Uranus is so dim, and the spacecraft was traveling so fast, that Voyager 2 had to pivot its camera platform during the long 15-second exposures to prevent blur. Just before the Voyagers launched, a system of rings had been discovered at Uranus. The planet presented a unique problem. Its axis is horizontal. Instead of north and south poles, it has an east and a west pole, and its moons orbit north-south. This meant that at closest approach, opportunities to photograph Uranus and each of its moons had to be crammed into a very brief period. While the surface of Uranus was featureless, its moons were varied, with the inner moon, Miranda, appearing as a confused jumble. As Voyager 2 passed Uranus, it looked back at the receding planet. On the morning of January the 28th, the Voyager science team had gathered to see the images and to review their results, when they paused to watch the launch of the Space Shuttle Challenger.
Space Shuttle mission, and it has cleared the tower.
Challenger, go with throttle up.
Roger, go with throttle up.
The disaster was to have far-reaching effects for NASA and planetary exploration.
My controllers here looking very carefully at the situation.
The shuttle fleet was grounded for more than 2 years pending an inquiry and a redesign of the faulty technology. More flexible, expendable rockets were reintroduced. Galileo was shipped back to the Jet Propulsion Laboratory, where it remained in expensive storage. Cost-cutting had resulted in a budgetary blowout for the Galileo mission. Galileo was finally launched from the shuttle in October 1989. Because of the launch delays, the spacecraft had missed the opportunity to receive a gravitational boost from Mars. The revised plan would first take Galileo towards Venus for a gravitational assist. This was less than ideal. The spacecraft had been designed to function in the colder regions of the solar system. Because it was passing through a hot environment, engineers decided to leave the high-gain antenna in its folded state until temperatures were lower. The next phase of its flight brought it back to Earth for an additional gravity assist. When Galileo began examining our home planet, it found an abundance of oxygen and indicators that life might exist on the planet. It returned valuable data on the state of the hole in the ozone layer. After the first Earth pass, engineers sent a command to deploy the high-gain antenna, but it was stuck. During the cruise, engineers tried spinning, cooling, and heating the spacecraft, but nothing worked. The antenna was designed to unfold like an umbrella, but 3 ribs were jammed. Engineers believed that more than 3 years in storage, plus 4 road trips across the United States, contributed to the malfunction. Without the high-gain dish, data flow at Jupiter would trickle in at a feeble 10 bits per second. In an unprecedented move, completely new software was developed that would enable greater data compression, but it would not be sent to Galileo until it had reached Jupiter. Ground stations were upgraded to work with the weaker signal. This would bring the data rate up to 160 bits per second. Still modest, but by recording data and images to the onboard digital tape recorder, the science team were confident of receiving a meaningful flow of information from Jupiter. Not long after Galileo's launch, Voyager 2 was approaching Neptune. This would be the spacecraft's final planetary encounter. It had been in deep space for 12 years and was showing its age. The ice giant at the edge of the solar system had fine streaks of cloud, and Voyager 2 registered the fastest wind speeds of any planet. Its blue tinge came from methane in the atmosphere. The Voyager's final target was Neptune's largest moon, Triton. It surprised everybody with an uncratered, varied terrain. It is geologically active, with Voyager seeing a nitrogen ice volcano. Voyager 2 then looped below the plane of the planets, heading in the direction of Sirius. To this day, after more than 4 decades, it still returns data about the environment beyond the solar system. The signals take about 18 hours to reach Earth. Through the 1980s, it had been the Voyager program that kept planetary exploration in the public eye. And finally, new planetary missions were being planned. Cassini was a joint venture between NASA and the European Space Agency. It was to go into orbit around Saturn, and like Galileo, it was equipped with a probe, called Huygens, that would attempt to land on Saturn's largest moon, Titan. Again, it had received political criticism for its billion-dollar budget, but with Europe bearing a large share of the costs, development proceeded relatively smoothly. Cassini was to be a flagship project. As it progressed, the new administrator took charge at NASA. Dan Goldin liked the planetary explorers, but he did not like the cost of Cassini. He called it Battlestar Galactica, but it was too late to change it. A Mars orbiter that had been in development since 1984 was also inherited by the Goldin administration. Eventually known as Mars Observer, it was adapted from an Earth-orbiting design. Like other missions, it had been delayed by the loss of the Space Shuttle Challenger. The delays meant its budget had expanded to more than $1 billion. Mars Observer finally launched in September 1992. But all contact was lost with the spacecraft just days before it was to go into Mars orbit.
Now, do you want to spend your remaining days in the space program?
When Goldin was given the top job at NASA, it was on the understanding that he would rein in what was seen by political leaders as a bloated and risk-averse management.
We're about leaving Earth.
His solution was faster, better, cheaper. A slogan and a strategy that encouraged innovation and risk, allowing some failure so long as there was a radical reduction in mission costs and a higher launch rate. Because interest in Mars was perennial, the Mars Exploration Program was established in 1993. 2 spacecraft were being prepared for the 1996 launch window, an orbiter called Mars Global Surveyor, and Mars Pathfinder with a lander and a rover. Both had budgets that were small fractions of former missions. Late in 1995, Galileo was approaching Jupiter. Months earlier, it had released its atmospheric probe. It would remain inert for months, staying out of contact with Earth till its internal clock powered it up, hours before entry. Problems with Galileo were frequent. When an anomaly arose, the spacecraft would go into safe mode, shutting down all but the most basic functions and then contacting the ground. Galileo was designed with a rotating portion and a static portion. Electrical contact between the parts was maintained via slip rings and brushes like an electric motor. Near Jupiter, the radiation environment and an abundance of dust played havoc with the rotary connection. Before Galileo slowed to enter Jupiter's orbit, it was scheduled to photograph both Europa and Io, and then record the data transmitted from the probe as it entered Jupiter's atmosphere. But a new problem occurred. The craft's tape recorder had been stuck in rewind mode for 15 hours before engineers noticed. When a similar problem was induced in an identical ground-based recorder, the tape broke. Without the recorder, the mission would fail. While Galileo's tape had not broken, the end of the tape would no longer be used. The recording of images of Io and Europa was shelved because the atmospheric data was just too important. Entry into the Jovian atmosphere went according to plan, and the subsequent atmospheric sampling functioned well. But because of the slow data rate, it would be weeks before the Galileo team began to see data confirming its success. An hour after receiving the last transmission from the probe, Galileo fired its main engine, allowing it to enter a highly elliptical orbit. This was the first time any craft had gone into orbit around Jupiter. During this 49-minute engine burn, Galileo made its closest pass of Jupiter, receiving a radiation dose approaching its design limits. Half the mission's radiation allowance was reached during this first orbit. The high apogee orbits allowed the craft to distance itself from Jupiter and its radiation belts. It was during the first high pass that the new software was uploaded to the spacecraft. It then began returning the data it had recorded from the probe while it dropped into Jupiter's atmosphere. The turbulent atmosphere features bands of wind circulating at different rates, with storms generating lightning 1,000 times more powerful than on Earth. Brief engine burns were used to adjust Galileo's orbital pattern so it could observe Jupiter's moons. During almost 8 years, the spacecraft made 35 orbits of the gas giant. Back at the Jet Propulsion Laboratory, NASA's first faster, better, cheaper mission was taking shape. Called Mars Pathfinder, it featured a small rover and a base station. It was primarily a technology demonstrator, with only a very small scientific package. For NASA, it was to be the standard bearer for the new approach to all the agency's space endeavors. Pathfinder would use airbag technology to land on the surface of Mars. Experienced engineers at JPL wanted nothing to do with the mission, so a cohort of young graduates staffed the project. At the same time, a different team at JPL was preparing the Cassini spacecraft for its trip to Saturn. Cassini represented decades of experience, all mission-critical systems backed up by onboard spares. The problematic tape recorder had been replaced with a solid-state recorder, and the high-gain antenna also had no moving parts. It took 6 years to build Cassini and its Titan lander, called Huygens, with the design process stretching back a further 10 years. Mars Pathfinder was given a small budget, and the designers were told to break with convention. Redundant systems would be dispensed with, and time-consuming testing was kept to a minimum. It had to be ready for the 1-month launch window in 1996, almost a year before Cassini would launch. Where they could, engineers building Pathfinder purchased off-the-shelf parts to keep costs down, and people outside the program had very little faith that it could work.
T-minus 10, 9, 8, 7,
The 4th of December,
3, 4,
1996.
5, 4, 3, main engine start, 1, 0, and liftoff of the Delta rocket with Mars Pathfinder. And the vehicle has cleared the tower.
This mission had a lot to achieve, and very few of its goals were scientific. Congress was not prepared to see NASA's budget keep increasing, yet Dan Goldin was convinced that by being creative, the agency could fly more without extra finance.
The spacecraft now is about 7,500 kilometers above the surface of Mars.
On American Independence Day in 1997, the Pathfinder was preparing for its landing on Mars, and Dan Goldin was present in JPL's Mission Operations Control Center.
Lander were pyrotechnically activated by guillotine-like cutters.
The elaborate sequence began unfolding as planned. As each new stage was successfully completed, the tension grew. Sensors within the lander registered 15 bounces.
I believe I have a firm signal.
Everything had gone according to plan. While the Pathfinder was only active for several months, it achieved all its objectives. The brand new Internet was awash with images from Mars as the tiny rover made its way across the Martian surface. The young research team began naming rocks near the landing site after cartoon characters. While some at NASA felt these names lacked gravitas, they were aware that the Pathfinder mission had generated huge public support, particularly among the young, and the decision was quickly made to follow up with more Mars missions. Faster, better, cheaper seemed to be working well. Mars Global Surveyor launched 1 month before the Pathfinder, but it was on a slower path to Mars. It was also a faster, better, cheaper spacecraft. Three months after Mars Pathfinder landed, the Global Surveyor arrived at Mars. It was to pioneer a new orbital technique called aerobraking. To slow enough to enter Mars orbit required a 22-minute engine burn. This put it in a highly eccentric orbit around Mars. Because its mission was to compile a detailed map of the planet's surface, it needed to be in a circular orbit. Conventionally, this requires extra fuel, which is extra weight, which is extra cost. By dipping into the planet's thin upper atmosphere during the low pass of each orbit, it could reduce the high point of its orbit without burning extra fuel. There were problems with a loose solar panel, but these were solved and the images returned by the Global Surveyor were sharper than anything yet seen. The spacecraft operated successfully for 10 years. Another plus for faster, better, cheaper. Late in 1997, Cassini began its flight to Saturn. The team was confident that Cassini was the most capable spacecraft yet launched. With a mission price tag in excess of $3 billion, it needed to be. While it was launched on the powerful Titan-Centaur combination, Cassini would still take 7 years to reach Saturn, as it needed gravitational assists at Venus twice and the Earth once. It launched with only a bare minimum of software. The team would use the interplanetary cruise to write and then upload the software needed for the orbital phase of the mission. Extensive hardware tests carried out during the cruise identified a design flaw in the Huygens radio receiver that would remain attached to Cassini. The receiver was too narrowly tuned. Relative movement between Cassini and Huygens as it descended toward Titan meant a Doppler shift in the transmitting frequency that the receiver would not be able to read. Spacecraft navigators had to rethink the planned orbital track for Cassini after the probe separation to reduce the Doppler effect to something acceptable to the receiver. In the 1998 window for launches to Mars, 2 more faster, better, cheaper spacecraft were ready for their journeys to the Red Planet. Lockheed Martin had delivered the 2 spacecraft for the price of 1.
2, 1. Main engine start and liftoff of the Delta rocket with Deep Space One, testing the spacecraft.
The Mars Climate Orbiter launched first, soon followed by the Mars Polar Lander, which was on a slower path and would arrive at Mars 2 months after the Climate Orbiter.
29 seconds, Mach 1, vehicle now moving transonic.
During the cruise to Mars, the Climate Orbiter proved difficult to handle. Its off-center solar panel was causing the craft to swivel under the influence of the solar wind, and daily thruster burns were required to keep the panel aligned. In addition, course corrections did not seem to have the desired effect. The navigation team could not understand why the Climate Orbiter was never where they expected it to be. This became a crucial issue as the craft approached Mars. Incoming data suggested that it would pass much closer to the surface than the navigators had expected. If it entered the atmosphere, the Climate Orbiter would burn and crash. Telemetry indicated that the insertion burn happened on schedule, but the spacecraft disappeared behind Mars 49 seconds earlier than expected. It was never heard from again. An inquiry revealed that Lockheed Martin was working in imperial units, pounds, feet and inches, while JPL was issuing instructions in metric units. Due to the slimmer nature of the faster, better, cheaper team, this anomaly went unnoticed. As the Polar Lander neared Mars, its team double-checked all systems to make certain that it would not be lost to another simple error. It had a more complex mission. It was to land near the Martian South Pole. As the entry, descent and landing approached, mission control at JPL filled with extra people. NASA Administrator Dan Goldin had made an appearance. The Polar Lander was not equipped to transmit telemetry during its entry and landing. Ground controllers lost contact with the craft as it was about to enter the atmosphere, and it was never re-established. There were various theories about the Mars Polar Lander's fate, but they were just speculation. An investigation led to the end of the faster, better, cheaper approach to planetary exploration. Yet the new philosophy had changed things at NASA. The Mars exploration program would continue, but with more rigor and increased budgets.
1. Main engine start and liftoff.
An updated version of the Climate Orbiter, known as Mars Odyssey, successfully went into orbit around Mars in 2001. It completed a detailed map of the mineral composition of the Martian surface, and it went on to act as a communications relay for later Mars missions. One of Dan Goldin's last initiatives was to give the green light to 2 much larger rovers that would use the same bounce landing technique as the Pathfinder. After a journey lasting almost 7 years, Cassini was approaching Saturn. The spacecraft's path looped upward between the planet's outer F and G rings. Crossing the ring plane could be hazardous, so Cassini swiveled to use its high-gain antenna as a shield. To enter orbit required a substantial engine burn. As this firing was a mission-critical maneuver, Cassini had a backup engine and complex fuel system plumbing that allowed engineers to bypass faulty components. It fired its engine exactly as programmed. Because the high-gain antenna could not point at Earth during orbital insertion, Cassini's only contact was via a steady, unmodulated tone from a low-gain antenna. Doppler shifts in the tone allowed Mission Control to understand exactly how Cassini was behaving. The engine shut down after the required 96 minutes, and Cassini became the first spacecraft to orbit Saturn.
4 years for this moment.
The usual jubilation tinged with relief followed. Very soon, a flood of images of Saturn's rings began flowing in. These pictures were recorded during the spacecraft's closest approach to the planet. The images were stunning, taken with solid-state cameras and replayed from a solid-state recorder. Previously, this technology had only been used in spy satellites. Late changes to the flight path, due to the Huygens radio receiver problem, meant that the Huygens probe's descent to Titan was delayed by 1 month. 21 days later, a timer activated its instruments just before Huygens entered Titan's atmosphere. During a descent lasting 2.5 hours, the probe sampled the atmosphere, measured wind speeds, and captured clear images of the Moon's surface. After a soft landing, it transmitted information for a further 72 minutes until it lost contact with Cassini. With minimal fuel usage, spacecraft navigators used the gravitational influence of Saturn and its major moons, enabling Cassini to follow a complex path through the Saturnian system. If interesting observations were made, the spacecraft's course was altered to allow it to collect more detailed information. The moon Enceladus had always been a target of interest. It is the whitest, most reflective body in the solar system. During Cassini's second pass of Enceladus, a peculiar deflection in readings from the magnetometer suggested that something was emanating from the moon. On a subsequent pass, Cassini flew just 25 kilometers above the small moon's surface. It flew through plumes of water vapor rich in salt with nanoparticles of silicon dioxide. This could only be formed with the combination of hot water and rock. Gravitational measurements detected an ocean beneath the icy crust. Tidal flexing from Saturn's strong gravity leads to heating of the tiny moon's core. Water vapor streams out through cracks near Enceladus's south pole. On Earth, volcanic vents in the deep oceans are able to support life, and all the evidence from Cassini points to a similar mechanism in the oceans of Enceladus. These discoveries led science to rethink ideas about where to look for life in our neighborhood. During the 13 years Cassini spent orbiting within the Saturnian system, it made 127 close passes of the moon Titan. Huygens had posed new questions about the only moon in the solar system with a thick atmosphere. It revealed rivers flowing on Titan, and radar mapping by Cassini showed substantial lakes, but these were not bodies of water, they were liquid methane. Planetary geologists think Titan resembles our own planet during its earliest days. Toward the end of its mission, as Cassini was running low on fuel, mission planners commenced what they called the grand finale. The spacecraft changed to a north-south orbit that, at its closest point, passed between the planet and its innermost ring. Saturn's major moons were now seen as so pristine and in need of further study that Cassini, with its radioactive power source, would be intentionally crashed into the planet rather than risk an unplanned impact. The new orbit revealed new views of the ring system. Their mass was calculated, and we learned that, particle by particle, they were falling into Saturn. The northern polar region, with its peculiar hexagonal weather pattern, was recorded in detail, and within it a polar vortex. Theories are currently being developed attempting to explain these phenomena. By September 2017, after close to 20 years in space, the end was near. The Cassini team had gathered to witness the final moments of a mission like no other. In Cassini, technology had finally caught up with the demands of long-duration spaceflight. Though problems had occurred, backups enabled mission managers to keep the very complex spacecraft functioning perfectly. Yet, while the engineering was superb, Cassini was a scientific tool that expanded humanity's knowledge about planetary physics and chemistry in surprising ways. Since Cassini, technology has continued to evolve, with more and more being asked of the new generation of spacecraft. To the end, Cassini kept transmitting data about Saturn's upper atmosphere until it was overwhelmed.